last few lectures, we have discussed about one-dimensional transient diffusion equation, solution of that using explicit scheme. We have also discussed the issue of stability in explicit scheme, and we have seen that the scheme is conditionally stable. Now, we are going to look two new schemes here. One is called implicit and another is Crank-Nicolson. Both of these schemes, as we'll see later on, they are unconditionally stable, and the schemes came as an outcome of research to improve the explicit method of solving one-dimensional transient diffusion. What we are going to do in this lecture is that first we will see the theory of the schemes, and then we will see some implementation in actual computer program. Very quickly I'll go through the program. We will not do the programming here. I have already written the program. I'll quickly walk you through to the structure of the program. So remember our discretization of one-dimensional diffusion equation, where the time derivative is forward in time, tin plus 1 minus tin, that is how we march in time, divided by delta t. But we have this problem that in spatial derivative, what should be the superscript of this t? This t, we will take them at what time level? Explicit scheme gives us an answer. It tells us that, well, you take this t at nth time level. Therefore, with this implementation, our discretized governing equation came just like this. tin plus 1 minus tin by delta t equals alpha by delta x square, ti minus 1 minus twice ti plus 1 at time level n. The stencil for this case was like this. We were calculating our value at this red dot, that is at n plus 1 time level, and already n at time level everything is known. To calculate this red, we need these three blues, which are all of them are at nth time level. Therefore, the difference equation that we developed here, left side the unknown has only one term tin plus 1, and right side everything is known. So essentially this algorithm leads to simple calculation, very easy to implement in an actual computer. Also in parallel computing, it's very easy to implement. Now, what we will do in implicit scheme is something very different. In implicit scheme, we will take up this right hand side t and we will say that, well, why do you take them at nth time level? Let us take at n plus 1th time level. The truncation error here actually doesn't change. They are still in delta t delta x square, but it changes something else. It changes the stability criteria quite a bit, but it also creates a completely new kind of solution approach. If we now take this n plus 1 left side and n on right side, so nth time level this is known and n plus time level is unknown. So you can see that we have three unknowns in this equation. So that's the problem now. Earlier we had only one unknown, we were calculating that. So now what we are going to do with these three unknowns? Here of course r is alpha delta t by delta x square. You look at the stencil, here we are calculating this red dot based on these three blue dots. Among these three blue dots, only one blue dot is at nth time level. Other blue dots are n plus 1th time level. Therefore, we have a problem here, how to solve it. But you think about it, it's not just one equation and three unknown. It's basically we will get three unknown in each of this equation. So for every unknown, we will get one equation. Each equation will involve, of course, three of these unknowns. So overall, we should be able to solve it. We have m number of grid points in X, and at n plus 1th time step, we have this m equation for m unknowns. So if I go along this, I have m number of grid points starting from 1 to m number of grid points, and in each of these grid point I'll get one equation like this. So overall I'll have m equations for m unknowns. I have to solve them simultaneously to get all the unknowns in one shot. So unlike the explicit method where every unknown we are getting from one of this equation, it will not work that way. Here we have to take all the equations in this n+1th time level, and then we have to solve them simultaneously. Each equation has these three unknowns, which means that this is going to be a tridiagonal system of equation. We already know how to solve tridiagonal system, and therefore it will not be a big issue for us. So here let us see that how we are going to implement this implicit scheme. This is our difference equation, that is RTI minus 1 minus 1 minus 2 RTI plus RTI plus 1, all are n+1 at time level. Right hand side I have minus TI at previous time level, which is known. Initial condition is T2, boundary condition is T1. So now the solution algorithm goes like it. Initially I have this initial condition Ti at time level 0 as T2 because it is coming from my initial condition. This is for all I. Then for n equal to 0, if I set n equal to 0, then from here I'll get Ti, that is first time level solution. So how we'll do it? For I equals 1, that is Ti1, that comes from our boundary condition T1. Similarly for I equals m, it comes from our boundary condition T1. Between this 2 to m minus 1, I have this equation here, that is R Ti minus 1 minus 1 minus 2 R Ti plus R Ti plus 1 equals minus Ti. This is at previous time level, so we already know it. Now you see that together we have enough number of equations to calculate all the T's. R also we know that this is alpha T by delta x square, so we can solve this TDMA, and once we solve it we get all T's at time level 1 for I equals 1 to m. So solution is complete here for n equals 0. Once this n equals 0 is complete, I go to n equals 1. Now the boundary conditions remain same because boundary condition is always T1. Here the equation is coming as R T2. These are not squared, these are T2. This is only showing the time level. 1 plus 2 R Ti2 R Ti plus 1 2. And here on the right hand side I have my Ti from time level 1, which we have calculated here, so I'll take it from here. Now again I see that there is a tridiagonal matrix system here. We can solve it and get it for this n equal to 1, the entire solution. Once n equal to 1 is done, we will go to n equal to 2, so on and so forth. So this is the way we are going to solve it. You can write a pseudocode for this and think about it, that how we are going to solve it. What I am going to do now, I'll quickly walk you through a computer program that I have written particularly for this scheme. You will see that how it actually follows the same result as we see in explicit, even though the solution algorithm is very different. So here I have a computer program for solving one-dimensional transient diffusion equation using implicit scheme. You can see here the program I have written is in Spider environment, and it is written in Python. It has an additional function that is TDMA, that is Thomas algorithm. We are solving tridiagonal matrix here, and then there is this main program. We'll come to the TDMA later, but let's look at the main program. Part of the solver is very similar to the explicit solver what I have shown you. The plotting part is the same, and here the exact solution I am calculating, that is also exactly the same. What is different here is that I am calculating this U from calling this TDMA. So in TDMA, I am giving this A, B, C, D. A, B, C are three coefficients, for one for Ti minus 1, B is for Ti, C is for Ti plus 1, and D is on the right hand side, the column vector. So we are giving this as input. Nx is the size of the matrix, and then we are getting the output. And again, next time in next time step again we will do so. So let us see. What we did is that is the same thing. What we have solved is this for this unknown U. Initial condition is 1 and boundary condition is 0 here. So I have set this U equals np dot zeros. That set the boundary condition. I am not changing anything at the boundary. Initial condition is 1. So U is my unknown, and I am putting this U equals 1. That is at 0. That is at 0th time level. U is defined at np dot zeros ntnx. This np is numpy array, and numpy array of size ntnx. At nt0, I initialize it with 1. That is the initial condition. Ux is the exact solution just as it was before. This A, B, C, D are the coefficients. In this case, even though they are constant, this program is written in general when it becomes function of x. Therefore, this A, B, C, D are initialized as numpy arrays of all size nx, and they are initialized as 0. Now, in this case, you know that for r equals dt divided by dx, here because I am taking alpha equals 1, this is del u del t equals del 2u del x2. So this is a non-dimensional equation I am solving. So alpha is 1. So r is delta t divided by delta x squared, and that gives a equals r, b equals minus 1 minus 2r, and c equals r. Afterwards, at a 0 0, b 0 1, because this is a tridiagonal matrix, then it doesn't have an a0 term. So at the top row, a0, this is at the top row. At the top row, we do not have an a. B is 1 and c is 0. There is no c term because my boundary condition is u equals 0 at top row. So u equals 0 means this b is 1, 1 multiplied by u equals 0 means d is 0, on the other side d, that is 0, and that sets the boundary condition at the top. Similarly, at the bottom, this nx minus 1, here also a is 0, c is 0, d is 0, because this is theta, u is 0 here. That is why d is 0 and b should be 1. B cannot be 0 anywhere. B are my diagonal element. So this is where we, in these two lines, we set the boundary condition. A is general expression of A, B, C is written here. Then A, B, C for first equation and last equation, they are the boundary condition, they are written here. D0 is 0, dnx minus 1 is also 0 because of the boundary condition. But other d's we didn't do anything. We have to do something about that. My d is on the right hand side, that is minus u from previous time step. So what I do here, I have this u old and u. U old is my previous time step value and u is my current value. So this is n plus 1 and this is n, that way we were discussing. So here as I get into the time loop, first I calculate the time. This time t is not important for numerical calculation, but they are important for this analytical solution where we have to explicitly give the value of time. Then I come to d. Because d is changing at every time level, d is equal to negative of u old will come from previous time level, and it is going between 1 to nx minus 2. 0 and nx minus 1, they are coming from boundary conditions, so we don't want to fiddle with them. Between 1 to nx minus 2, it is negative of u old, so that is how I have set my d. My ABC is set here once, and I will not change them again, because in this particular case ABC are constant. If ABC are functions of u or x or something, then you may have to update them, but you will not update them here. Therefore, I have set up my D here, so my A, B, C, D are known. I can now go to TDMA and solve for the unknown. That unknown I have named it as U old. You can as well give it as U, and then that U old, and I am bringing this U equals U old. This is U at nth time level is equal to this U old. Now it will again follow this loop until this nt minus 1 is achieved. So now we can go and look at this TDMA. In TDMA algorithm, I am taking this ABCD, and nx is the size of the matrix, and I am solving for this unknown. In this case, I have written here V. This ABCD, what I have taken, I am not changing the ABCD itself, because this ABCD will change in Thomas algorithm. What I am doing is that I am copying them in another variable, because Python has this convention that it will change the array that I am bringing from main to a function. If I change this array inside the function, it will change it within the main. I don't want to do that, because my ABC, I want to keep them just as it is. D can change, but ABC cannot. Therefore, I have just copied all of them in A1, B1, C1, D1, and what I am doing here with this only with A1, B1, C1, D1. So this is our old Thomas algorithm. Here this B1 is changed, that B1 is equal to B1 minus this A by BI minus 1 multiplied by CI minus 1. So that is what I am doing. This is the forward part. I am changing this B and the D. Then I get the last V by itself, because in last V there is only diagonal element and nothing else. So I can get it, and then for subsequent V, I have to come back from n minus 2 to minus 1, and this is how I am calculating. This is the back substitution part of my Thomas algorithm. Now you may not remember Thomas algorithm right now, so you can stop the video here and go back and look at the lecture notes on Thomas algorithm. You see it, and then you come here again and try to understand the program. So from Thomas algorithm, I am getting this U here, and every time this TDMA will run once. So the calculation is much more involved than the explicit calculation. Once this calculation is done, I am calculating here the analytical solution exactly the way I did it before, and then I am plotting the results, analytical versus this implicit solution. So you can see that we can run this and see that how it goes. So we are running it here, and you can clearly see that it ran for a couple of seconds, and then it has given us this profile. Here this is theta, it should be U actually, so I have put theta here, and this Z. So then this red dots are my numerical solution, and this lines are my analytical solution. So you can clearly see that these red dots are falling exactly over the line, and that way I can say that my numerical solution and analytical solution, they are going well, as we have seen in the explicit solution. So the result wise, there is not much of a difference between explicit and implicit solution, at least for our case. However, as we will see later on, that it will be more stable scheme. So now we have seen both explicit and implicit methods. Here in explicit, the right hand side is discretized at nth time level like this. In implicit, the right hand side is discretized as n plus 1th time level like this. Now we can combine these methods and we can get new methods. Like what? Like introducing this scalar quantities P and Q. We take some part explicit, some part implicit, and that way we can combine. You will see that as long as P plus Q equals 1, many such schemes are possible and they will give reasonable result. So all these schemes, how do they make it, or are these schemes really they are good schemes? Well, that you have to run them and you have to check for yourself. But to use any scheme, we know that the starting point is that you have to see for stability and consistency. If any scheme is stable and consistent, you can try and use that scheme. The accuracy of the scheme is not guaranteed, that you have to see that how accurate they are. But as long as they are stable and consistent, they are usable scheme. So many such schemes are possible. And one such scheme is particularly popular, that is what we call this Crank-Nicolson scheme, which is this P equals Q is 1 by 2, which means half of explicit plus half of implicit. That is how we take it. So here, this is the same Nicholson who actually looked into the problem of explicit methods, and she gave a solution that how we can have a better method that has a better stability. And from that, this Crank-Nicolson method came into existence. So what kind of method is this? So here, as I said, that the right hand side, the half of this is explicit. So here you see that these are nth time levels. So this is explicit. This is half of alpha multiplied by this. Similarly, half of this, once again alpha by 2. This is implicit, n plus 1th time level. The interesting fact of this is that here, unlike other schemes, this has a truncation error of the order of del t square and del x square. It can be done, it's a long process, but it can be seen from a Taylor series analysis. So if we now try this, how this solution algorithm will look like. So let's first develop the difference equation. The difference equation will look this way. I take all this n plus 1 other side. So left hand side, it looks like very much the implicit scheme, only this r by 2 and 1 plus r etc. were coming. Earlier it was r, 1 plus 2r, r. It was something like that. On the other side, you see that all these nth time level terms will be there. So this 3 terms as well as 1 term that will come from here, this term will go on other side. Together they will create 3 terms on the right hand side, unlike implicit where there was only 1 term on the right hand side. In the stencil, it looks like this. I have this rate point I am calculating, and it requires 1, 2, 3, 4, 5 other points. 3 points are from previous time step and 2 points from this time step. So it's essentially the same procedure once again, just like the implicit. We have to build up all the equations here at n plus 1th time level, and then we have to solve them in one shot using a tridiagonal solver, because every equation has 3 unknowns now. So at n plus 1th time instant, we have m equations for m unknown, but each equation has 3 unknowns. So once again, we will use our tridiagonal solver here. What would be the algorithm? Well, it would be very similar to the implicit algorithm. We are starting from the initial condition T2 and boundary condition T1. So here this initial condition is this T2. I give this Ti naught equals T2. This 0 is the time level. Then for n equals 0, that means I'm calculating for T superscript 1. Between I2 to m minus 1, I have to solve this equation. For I equals 1, I equals m, I apply boundary condition T1. Here I solve this equation very similar to implicit equation, but right hand side is different, and R, it was R here in implicit, it is coming R by 2, it was 2R here, it is coming R, etc. So we solve TDMA and get for time level 1. Once we get time level 1, we can move forward, and we at n equals 1 we follow similar procedure as we did in n plus n equals 0. This right hand side will change because the time level here is changing. So at every time level we have to use this TDMA as much as we did in implicit method. We have to do that, and then finally we'll get the solution up to our desired time level or up to the steady state. So let us now quickly see that how we can modify our implicit program and make it a Crank-Nicolson. That should be a very trivial exercise. Once you write the implicit program, then making it Crank-Nicolson only means that I have to change this part. So it's a very trivial exercise. So let us check it out. So what you see here is the Crank-Nicolson program, and here I had the implicit. So compared to implicit, there will be not much of a change here. The right hand side will change, and we'll do that change. And also this ABC will change because R will go by now R by 2. So what I did here is that I simply here I have simply kept this ABC same, but I have changed this R as dt by twice dx dx. In implicit it was dt by dx dx. So I kept this same. For the right hand side I was setting it from here, that was u old 1 to nx minus 2. What I did here is very similar, but here I have 3 terms. So for this d 1 to nx minus 2 is that will be this u old 0 to nx minus 3. So this is I minus 1. This is I 1 to nx minus 2. And then this is I plus 1. So 2 to nx minus 1. Then I am, once again, this is the same thing. I am going to this TDMA and I am calculating this u old. Then u old is my u at nth time level. Here I am calculating the exact solution, and then I am plotting exactly the same thing as I was plotting in explicit or implicit. So let us run the case and see what happens here. So I'm running it now. You can see that it gives exactly the same result as my explicit or implicit. Here the lines are analytical solutions, and this dots are my numerical solutions from here. The quality of solution may improve or may go down depending on grid sizes, but overall you can see that all 3, implicit, explicit and Crank-Nicolson, they are working very well in solving numerically the one-dimensional transient diffusion equation. So now we are ready to summarize what we have learned from this lecture. We have studied both implicit and Crank-Nicolson scheme for 1D diffusion. The Crank-Nicolson scheme, even though we have not proved, this is a tedious proof, but you can try it using Taylor series expansion, that Crank-Nicolson is second order accurate. So we have a second order accurate, and it will also be unconditionally stable scheme. So this is a very good scheme. The stability we have not seen yet, but we will see it later on. So a scheme that is highly accurate as well as stable, certainly this is an advantage over other schemes. For your exercise, you write a pseudocode for solving one-dimensional diffusion equation using Crank-Nicolson scheme. So that's all for this lecture. Thank you, and I'll see you in next class.